Hello, I'd like to welcome everyone to this plenary session featuring Hiroo Kanamori. I'm Jim Mori and I'm here with Annemarie Baltay as chairs of this session. Hiroo needs no introduction as one of the most foremost seismologists of our era, and I think everyone knows him at least by name. He's received most of the major prizes and honors for seismologists and geophysics, including the SSA Reed Award in 1992. Unfortunately, you cannot speak to him directly this year, but with today's session, we'll let you ask questions and anything you'd like to ask him online. Today, he'll have a short video talk for about 25 minutes, and then video talk for about 30 minutes, and then we'll have questions for about 25 minutes. You can submit questions on the chat section during the video or after it when we're in this question session. So with that, why don't we go ahead and watch the talk by Hiroo.
Okay. Now, earthquake is a very complex fracture process. To understand such a complex system, it's useful to consider two end-member systems. One is isolated system, essentially single fault like this one. And this one is deterministic because it has very definite scale lengths. One is fault dimension, the other one is plate motion speed. And for that reason, this system is reasonably predictable. Of course, there are some heterogeneity and nonlinearity, so there is some fluctuation, but overall, it's deterministic. The other end member is a large system with many interacting pieces like this one. And this is a typical chaotic system, and behavior is non-deterministic. And it's predictable only in statistical sense. So overall behavior is very erratic here. So it's very difficult to predict deterministically. Well, let's first show you a deterministic case. This is a real example. A Kamaishi repeater studied by Tohoku University group. There are about 10 events since 1950s, all magnitude 5, separated by 6 years. These are the sequences. It's very regular, and the waveform is almost identical from event to event, meaning that the source is almost identical, just repeating. And the other extreme is the complex interacting system. Example is 2004 Sumatran earthquake. It ruptured from here all the way to the north over nearly 1,500 kilometers. The reason why it was so complex is it has many slip patches in the subduction zone. And when one patch failed, it triggered the other one, and so on. So it's a sequential occurrence, and it's hard to tell exactly where it stops. That's the example of a complex system. And the real earthquake sequence is in between, and that's why our system is so complex. Well, this is a very beautiful picture taken by Dr. George Pravka. These are marine terraces in Middleton Island, Alaska. You can see 6 terraces, 1, 2, 3, 4, 5, 6. And the lowest one was formed during 1964 Alaskan earthquake. And if you make a plot, this is a terrace height as a function of age. They are not identical. Interval ranges from 500 to 1350, and the height ranges from 3.5 to 9 meters. So nothing is completely regular or random. However, overall, we have this repeating sequence, and this is what nature tells us. Well, how to study this one? This is a photograph taken in the 1950s at the Seismological Laboratory, Caltech. They were interacting each other. Press Gutenberg, Benioff, Richter, with all different expertise, and they are looking at seismogram to understand something. So this is a kind of very important interaction in doing science. And unfortunately, for the last year or so, because of pandemic, we lost this kind of opportunity. So it has been a very difficult time. Well, Gutenberg actually studied every single earthquake like this. He is reading seismogram. However, at the same time, he was looking at station bulletins. Every event, hundreds of events. And with Richter, they published a monumental work, Seismicity of the Earth. This is a very impressive work. He looked at all the station bulletins and read station time residuals and fit sine wave nicely and relocated every event. And also he looked at the station bulletins amplitude report for body wave and surface wave and estimated body wave magnitude MB and surface wave magnitude MS. And this is a complete study, and that really is the basis of present-day seismology. Well, a classic example of scaling relation based upon these things is the one by Utsu and Seki. And they plotted a log of aftershock area A against magnitude. As you can see on the scale, you can see general relationship, straight line. And this is a general trend. However, you can see some outliers scatter. And this is the nature of the process. In modern days, we use slightly different quantity. Instead of magnitude, we often use seismic moment. And instead of area, we often use length scale L and also time scale tau. But basically, this kind of relationship is really the basis of seismology even today. Well, these are the modern recent scaling relations. This is a scale radius or dimension versus seismic moment. There is again straight line, as we saw in Utsu-Seki relationship. The scatter is very large here, but it gets smaller towards large magnitude. This is a similar plot. Instead of scale, length scale, now time scale here, log tau versus log moment. There is a trend giving ordinary regular earthquake and give another trend, maybe for slow earthquake, but slow earthquake can follow this trend too. So this basically tells us they follow some rule, but maybe with different parameters. This one is another parameter, radiated energy over seismic moment we call scaled energy. This is plotted against 19 orders of magnitude of seismic moment. If you look at this diagram from some distance, you can see essentially flat constant. So we say it's constant. However, if you look at the scatter, it's 4 orders of magnitude. And obviously, this large scatter includes some noise in the data and some error in the analysis, and also the real variation. And so there are uncertainties in the interpretation, uncertainties in the data. But it doesn't matter. What is really important is to have this kind of relationship, which gives us a basic data for understanding rupture process of complex system. Well, so the rules is important, and that's a key to a better understanding of rupture process. Well, let's look at the macroscopic process and the microscopic processes of earthquakes. A macroscopic process in seismology is slip D, the radiated energy ER, stress drop change, delta sigma, and so on. And these are observables. But interface sliding is very complex. This is where earthquake happens, fault plane. We have microscopic processes, deformation, fracture, heating, lots of things. So associated with those, we have dissipated energy E sub D. So obviously, this is a very important quantity. Unfortunately, in seismology, we cannot measure these things directly. So we have to keep in mind there is some uncertain element in this kind of model. And this is a subject of theoreticians, laboratory people, geologists. So it's a very active research area, but I concentrate here on seismology part. Seismological observable is radiated energy. This is the most important parameter in this kind of study because this is how we see an earthquake. Okay, so let's summarize microscopic source parameters in the order of robustness of determination. Seismic moment, this is very well determined, very accurate, at least for large events. Radiated energy, very important for interpretation. Unfortunately, it's too challenging to estimate energy very accurately. Time scale, or speed of something, like rupture front speed, and length scale, and delta sigma. Delta sigma stress drop is very difficult to determine, and it's loosely defined. So we have to be very careful in using this one. Another class of seismic observable is moment rate function. This is essentially source time history or spectrum. If you take Fourier transform, you get moment rate spectrum. So this observation is very important because we can understand what's happening at the source as a function of time. So these are the parameters we are going to use. Well, this diagram is very often used by seismologists. The vertical axis is the stress on the fault plane, and the horizontal axis is a strip. And this straight line is what we call stiffness curve. And that corresponds to spring constant. And if the force is balanced against friction completely, the motion is quasi-static and the slip follows this trend. In this case, the entire strain energy is dissipated and no seismic radiation. So this is a silent earthquake or plate motion, no really radiation, no seismic waves. The other end member is this. The stress drops from sigma naught to sigma 1 instantly and slips at constant stress sigma 1. So this is a very abrupt process generating a lot of seismic waves. So strong shaking and a large energy moment ratio. So this one and this one are the two end members. The real earthquake is somewhere in between. This is an example. And this behavior is governed by sigma as a function of delta. And for most earthquakes, this ratio turned out to be 10 to the minus 5. So the slow earthquake people are talking about are probably around here, and the silent earthquake is almost on this line, and very, very violent earthquake may follow like this one. To understand this situation better, I use Kikuchi's very simple conceptual model, sort of slider block coupled to continuum. Well, the same diagram here. This is stress on the fault or stress in the spring, and this is a slip. And the three typical cases are shown here. This blue one is a strong earthquake I mentioned. Stress drops very abruptly to this level. And the displacement is very sharp because the stress drop is so abrupt. And the velocity is very large because it moves very rapidly. And energy moment ratio is very large. Okay, and this red one is a slow earthquake I mentioned. This follows more or less this quasi-static curve here. In this case, slip goes very slowly like this one, and then velocity is small like this one. And energy moment ratio is very small. And this one is intermediate right here. So this is a very simple conceptual diagram that links seismic observation like ER over M naught to the physical mechanism occurring in the Earth's fault. So this is a very useful diagram for understanding, and the actual process is, of course, far more complex. Let's look at the example. This is a cross-section of a typical subduction zone. This is subducting boundary, this is upper plate, and this is the lower plate. Well, the standard event, Vegas thrust earthquake, which happens on the boundary, and this is a tsunami earthquake that happens near the trench here, and also intraplate events like here and here. And of course, they happen in a different environment, so the physics can be very different. Accordingly, energy moment ratio is different. This is the energy moment here as a function of magnitude, the same kind of diagram I showed you before. So if you look at this diagram at some distance, then you can say it's essentially constant like this. However, if you look at it carefully, these three different types of events have different group, like here. Intrastellar events have highest ER over M naught. Tsunami earthquake have lowest ER over M naught ratio, quite different, one order and a half magnitude difference. And the megathrust is in between and pretty constant here. So this basically shows this seismic observable ER over moment can be used to interpret where the earthquakes are happening, or the physical environment and the process associated with it. However, in order to understand it, you need to have a model. Well, this is the cross-section of subduction boundary and Nankai trough. And actually, plate boundary is not a simple plane. It has some structure, subfaults, and complex fractures, and so on. So basically, earthquake process happens in a zone rather than on a plane. And the tsunami earthquakes, which happen here, can deform the medium and also produce some cracks and others. So large energy dissipation can happen. A megathrust event happens at some depths, so it's simpler, so energy dissipation is less. And the intraplate events happen over here that happen in a more homogeneous medium. Therefore, ER over ratio can be very high. This is a sort of intuitive interpretation, but of course, it's very useful to come up with a model to explain this quantitatively. There are papers by Ma and Hirakawa and Lambert and others, and many others, and they talk about individual processes that can produce this ratio ER over M naught for different mechanisms. And these studies are very useful for understanding the process. Seismologists can take only microscopic processes. Okay, so as you can see, the estimation of energy is extremely important because without understanding it, we can never understand the process. However, as I said, it's very challenging to determine energy with high accuracy. Well, since 1920s, many efforts have been made. In 1920s, Galitzin and Jeffries studied 1911 Pamir earthquake, and they came up with the energy value. Those values are different by factor of 250 from here to here. Well, factor of 250 is a bit too large to be used for a quantitative interpretation. And Gutenberg and Richter recognized the importance, and from 1940s and 1950s, after revision and revision, they came up with some estimate, but still the uncertainty was an order of magnitude to nearly 1.5 orders of magnitude. So that was still not quite enough. But since 1980s, with the advent of broadband seismic data, and the method, the situation improved quite a bit. And these are determinations by different groups here. And there is some scatter. Up until a few years ago, there was still scatter of about factor of 10. Well, 10 is much better than 250, but still not quite good enough. So we have been really trying to reduce this to maybe factor of 2, 3, or even 1. Why is it so difficult to measure energy? It sounds simple. However, it's difficult because the Earth is essentially opaque. All the energy can get dissipated in the path. For example, at teleseismic distances, for magnitude 6 earthquake, only 9% of the radiated energy is observed, and the remainder 90% is lost during propagation. So you can't really estimate energy very accurately. If the magnitude gets bigger than 7.5, it's much better. 80% of the energy can come to the observation station. But in addition to attenuation, we have near source scattering, near source path effects, site response, all kinds of complications. That's why energy estimation is so difficult. Well, we did some experiments recently. Japan has very nice network, KickNet, which has a surface station and downhole station at 200 meters to sometimes 2 kilometers or 3 kilometers. So we can record, we can see the waveforms at downhole, this black curve, and the surface, the red one. Same earthquake, same station, the amplitude is nearly factor of 10 different, just 200 meters apart. One is on the surface, the other one is at the hole. Well, for energy estimation, we have to square it and integrate. So this ratio can be off by more than 100. This is another one, Totori earthquake, the same thing. So if all the stations are like this one, we have factor of 100 uncertainty in energy estimation. That's almost impossible to use. These are extreme cases, however. And other cases, maybe factor of 10, factor of 2 or 3 in the best case, but still the error coming from this one is really very large. So that's why we still have uncertainty. So we try to use this downhole stations available in Japan, and I hope we have been able to reduce the uncertainty to maybe factor of 2 or 3, and someone can improve it from now to make 1. Well, let's talk about outliers. I talked about outliers. Well, outlier 1, there's a tsunami earthquake, a very early pioneering work in Japan, Iki, Imamura, or Mori. It was very obvious this 1896 Sanriku earthquake was a very slow earthquake because it was very felt on Sanriku coast. People didn't pay much attention to it. However, 30 minutes later, 30-meter tsunami came to the shore, killing more than 20,000 people. So without any instruments, well, actually there are some instrumental records, but basically observationally, this was a very unusual outlier in the sense that high frequency energy was very small. This is another example from Professor James Mori, 2006 Java tsunami earthquake. Well, heavy tsunami damage, obviously, deformation was very large at long period. However, this even flimsy looking building came through without much damage. So shaking must have been fairly modest. So this is again a slow tsunami earthquake. However, for seismologists, it will be more satisfying if you can look at the actual seismic wave and measure everything quantitatively. So I can give you just one example. There are 2 events, 2020 Oaxaca event, 7.4. This is a regular earthquake. A 1992 Nicaragua tsunami earthquake. It's a famous tsunami event, magnitude 7.6. And I compare the waveforms at the same station, ESK. At a very long period, as you can see, 700 to 1,000 second amplitude and the waveforms are pretty similar between regular event and tsunami earthquake. All right. So at the period of 20 seconds, tsunami earthquake amplitude is only 1/5 of the regular earthquake. At 5 seconds, you can't even see it here. So this simply says tsunami earthquake has a very weak high frequency radiation compared with long period radiation. So this is observational data, and it's very nice these days that we can determine this quantitatively very rapidly so that we can understand this kind of difference. Well, let's go to outlier 2, long rupture. I mentioned the 2004 Sumatran earthquake. This happened here and ruptured to the north over nearly 1,500 kilometers. And there are many slip patches here, and these patches were triggered one after another, so that this event here actually grew to this large event with large magnitude 9.2. A similar event happened actually in 1906 in Colombia, Ecuador. This area seems to have 3 patches like this one. They broke 2016, 1942, 1958, and 1979 separately. However, in 1906, apparently the whole thing ruptured together, producing very large events over here. Okay, a similar event happened along Nankai Trough. In 1946, 1944, magnitude 8 events happened 2 years apart here, from here to here. However, 1854, these 2 events happened about 30 hours apart. In 1707, they happened simultaneously in a single event. And the 1605, this whole zone apparently ruptured as a tsunami earthquake. So we can see this triggering interaction as well as some difference in the rupture zone. So this kind of variation is hard to predict. And we often have this kind of outlier, which is very hazardous, like 2004 event. Well, again, for seismologists, it's nice to see the actual waveform to see how different they are. This is actually moment rate function, source time function in the order of increasing MW going this way. So as the magnitude increases, it gets longer. All right, this is 200 seconds. So as the magnitude increases, the duration increases like this one. Well, look at the 2004 Sumatran earthquake. This is very long, nearly 500 to 600 seconds from here to here. 2011 Tohoku earthquake, about the same magnitude. However, this duration is about 120 to 150 seconds. So there is a big difference. The reason is 2004 Sumatra earthquake is a long interacting events. One event triggers adjacent one and so on. So we can see again instrumentally very clearly the difference, and we can study these things in detail so that we can understand some rupture physics from here. Outlier 3, well, this is a slightly different kind of outlier. It's a site response I mentioned already. Sometimes site response is spectacular. Well, this is a case for 2011 Tohoku earthquake. There was a 52-story building in Osaka Basin in Japan, 256 meters high. And there were people on the roof at the time of the earthquake. And those people were really scared and surprised because this roof swayed 1.37 meters due to this earthquake 800 kilometers away from here. It's very surprising. And the basement, at the base of this building, the displacement was about 9 centimeters. So from here to here, there was factor 14 amplification. So that is surprising in a way. However, technically, this is not at all surprising because building is a kind of pendulum. And when the period matches here, it can resonate and the large amplification happens. So from here to here, it is surprising, but not surprising. What is most surprising, however, is why this whole thing happened. Well, this is the waveform at Sendai and 2 kilometers beneath surface in Osaka, 800 kilometers apart. So this is a ground motion in Sendai, this much. And as it propagates from here to Osaka, the amplitude decays 1/30th. So it's very small. This decay is very natural. It's a long propagation distance, nearly 800 kilometers away. Then this was multiplied, amplified by a factor of 30 going from 2 kilometers here to surface. This is surprising. This is a site response. And also the waveform changed from here, from Sendai. It's almost harmonic 6-second wave. That's why the building was shaken by resonance. Well, there's a paper by Sato and others. They showed that this whole thing happened because of source path effect and site response. So it's very nice. The seismology can explain this kind of rather surprising observation. So it did happen. So it can happen in the future too. But luckily, in this case, the building survived. It was used even after the event. Well, it was okay, fine. However, what will happen if the ground motion much bigger than that comes to the base of this building? What happened is 9 centimeters here, 1.37 meters sway here. If the displacement here is, say, 1 meter, what will happen? Well, actually, that's such a large ground motion did happen during 2015 Nepal earthquake. Nepal earthquake produced a large ground motion at Kathmandu, 77 kilometers away. This is a record. If you compare this with the Osaka record here, 9 centimeters, it's almost 10 times bigger. And Nepal earthquake is 7.9. And in case of this building, just next to it, there is a site potentially for a magnitude 9 Nankai earthquake. So this kind of thing can easily happen probably if there is a site like Osaka Basin. So the obvious seismological question is, 9 centimeter produced 1.37. What will happen if we have 1 meter ground motion like this comes to here? This is a difficult question. And this question is far beyond my expertise, so I can't answer this question. However, engineers studies this very well. And there's an interesting paper by Hayashi and Sugino, and they came up with very interesting analysis. And if you are interested in the answer, you should read this paper. Well, outlier 4 is mechanism. This is a very unusual thing. And we have been working on the 1960 Chilean earthquake, the largest event recorded instrumentally. And this is believed to be essentially a thrust event caused by subduction of Nazca Plate beneath South America. And that's probably true. However, after looking at some old strain meter record, we came up with the idea because that the source cannot be simple thrust. It must have some large strike slip component. Event that produced that the strike slip could be nearly magnitude 9 or so. This is a bit surprising conclusion. And of course, any result with all the records can be uncertain. So we have to worry about it. But at least so far, it looks like there was strike slip component. So in order to show another evidence, we looked at the record from 2016, almost pure thrust event in the Chilean subduction zone here, very close to the location of 1960 Chilean earthquake. And that record is very interesting. Well, this slide shows the strain extensometer here at Ogdensburg or 1960 Chilean earthquake. And you can see very large G wave with respect to Rayleigh wave here. And the G wave is transverse wave, and the instrument is extensometer. It's rather rare to see large transverse wave on the extensometer. And this led us to the conclusion that 1960 must have had very large strike slip component. Well, how about 2016? There was a nice record at Harvard, very close to Ogdensburg at this distance. If you simulate a strain record for this one, we come up with this one. There is no numerical computation. It's basically made from observation. As we expected, G wave is very small and is smaller than R2, and more or less noise level here. It's very different from the situation from 1960 event. So this simply means that this is very different. Okay, so what are the implications for hazard mitigations? If outliers are very unexpected, we have to come up something to really deal with it. One approach is a scenario earthquake approach. And in that case, we can include the results from all possible outliers. So this is a very useful approach. The second one is to use real-time technology. Okay, recently, the Japanese government made a scenario earthquake for Nankai Trough. This is a 700-kilometer stretch along the Nankai Trough. And they came up with scenario earthquake that includes tsunami earthquake here near the trench, that includes a low frequency earthquake near the bottom, and includes possible extension due to interaction, and also complexity in geometry. I would rather add strike slip component too, because there are some inland strike slip force like here. So anyway, this kind of scenario earthquake can take all the unusual features. So it's very useful for hazard mitigation purposes. Well, the next step is, of course, how to communicate this to local government and the public. And of course, we have to come up with a strategy to deal with this one. And again, we need help from engineers to do that. How about real-time methodology? Of course, in the past, advances in instrument, network, computer, and telemetry, now we can do seismology much better. And by using this one in a way, the Earth is essentially a set of eigenfunctions and eigenvalues, so we can use them to compute ground motions very accurately and magnitude and very rapidly. So this technology can produce real-time methodology, both mechanism and ground motion strengths. Well, this slide is made using input from Hauksson and Hoshiba. Basically, this shows speed, processing speed as a function of time since 1920. In the 1920s, it took many weeks, many months sometimes to study these big earthquakes. So you can't use this kind of information for real-time application. However, these days, we can determine ground motion tsunami type warning, make tsunami type warning in a matter of a few seconds to a few minutes. This is a trend at Caltech for location and magnitude. Now we can estimate these things within a few minutes, and with the mechanism, we can estimate in 10 minutes or so. JMA can make tsunami warning in a matter of maybe 20 minutes, 30 minutes, and many earthquake early warning systems developed by many countries. Now we can tell ground motion in a few seconds to maybe 20, 30 seconds. So the goal would be somewhere over here. So we are approaching to the goal. It will still need some progress, but at least we are making progress. Again, the next step is how to use this real-time information. Again, we need to develop some technological advancement. We need technological advancement so that we can use real-time information more automatically so that we can make good use of it for protecting properties and human lives. Okay, these are the conclusions, somewhat obvious. I will read it. Number one, earthquake process has deterministic and non-deterministic elements. Number two, effective hazard mitigation practice must consider both. Number three, modern seismology can determine many source parameters accurately and rapidly so that we can understand rules and outliers very quickly and also use them for real-time purposes. A scenario earthquake approach and real-time hazard warning can be very effective for dealing with outliers. Number five, still we need better preparedness, communication, education, and drills. These are very critical for long-term hazard mitigation. Many countries are doing this. That's very good. Number six, this is more or less my personal opinion. Well, seismology is intellectually very exciting and satisfying. It is satisfying because it has direct relevance to society, and what we do can potentially save lives, or even a single life. And this makes our life very unique and worth living. That's exciting. Well, thank you for listening to an old-fashioned presentation.
Okay, well, thanks for the talk, Hiroo. And we have them online here. So we're open for questions. So please use the chat session to submit any questions and I'll relay them to Hiroo. To get things started, Annemarie, why don't you give the first question to Hiroo?
Great. Yeah, thanks so much. That was a fantastic talk. And I really loved the very ending about your personal opinion that seismology is intellectually exciting and satisfying. I totally agree. So the first question that I had are, can you think of, or are there any interesting slow earthquakes that occurred down dip that might have been tsunami earthquakes had they been shallower? So is the unique slow rupture behavior a consequence of being shallower due to some physical property, confining pressure, lower coupling, or compliance zone? Or do we also have slow earthquakes deeper that are not tsunami events?
Well, in case of San Andreas, for example, some fairly deep slow earthquake. But recently, a group at Kyoto, Professor Nishimura and his colleagues found very slow events, very slow slip in the Sine region behind Nankai Trough. And in that case, small slow earthquakes had been found by Ide and others. So there were some slow events at depths, around 30 kilometers or so, also Kyoto Bosai group too. So basically, slow earthquakes are happening all the time, but mostly slow earthquakes at depths are much smaller than, say, magnitude 7 or magnitude 8. So basically, in terms of slowness, they are comparable to tsunami earthquake, but simply the difference in size makes it very different.
Great.
And
Jim, did you want to ask the next one?
did you want to follow that up or?
Oh, sure. Yeah. So I guess a follow-up there here, that's great, is that, does there mean there's some like forbidden zone that at depth you could have regular earthquakes or really slow slip? But I think you said that there have been some slow earthquakes at depth, just smaller magnitudes, they're harder to observe. Do you think there's a smooth transition, or are there some depth dependent properties that forbid certain behavior?
Well, it looks like, you know, on subduction zones, it looks like reasonably gradual. The megathrust, it's more brittle, but as you go down, it becomes slower. And also, even within ordinary seismic events, there is a difference between Outliers events and subduction megathrust. So there are different environments where different types of earthquakes happen.
Okay, we have a question from Jack Muir. He said, thanks for the talk, Hiroo. For the Kickneck borehole stations, is it possible to predict the observed amplification from the seismic structure using, for example, well log data?
Well, that's a good question. We wanted to understand why such a large magnification can happen. And in some cases, it's only 200 meters that makes that big amplification. So I suppose if you really know the structure reasonably well, and in case of Japan, they do know. So I guess it's possible to at least make a reasonable good estimate of the amplification. But I don't know whether someone has really compared computer waveforms with observed waveforms. In many cases, where the amplification is really large, it's pretty harmonic. So certainly we are seeing the clear structural effect. But I don't know whether there's any really definitive comparison.
Okay, we have a question from Luciana Astiz. Can you compare subduction zone earthquakes with intraplate, interslab earthquakes, which may have higher frequency content? And how do you account for them in hazard maps?
Well, in a way, the subduction zone we would call Outliers events, intraslab events, and also there are some deeper intraslab events around 50 kilometers or so, and there is a clear difference in the spectrum, and also the integrated energy, it's very different. So the spectrally, it's very different, and well, recently we are using very old-fashioned parameter like MB, Gutenberg's body wave magnitude, and there is a clear difference between intraslab events and subduction zone events. Subduction zone event means megathrust events. So there is certainly a very significant difference in the strength of ground motion between events from two different environments.
And how about, how does that affect the seismic hazard maps, do you think?
Well, that's a higher level of this difference. And at this moment, I'm not sure whether that type of difference is included in the hazard map or not. And the hazard map is certainly a very useful approach, but there are lots of parameters which should be included, not only the magnitude and location. There are lots of spectral differences.
Okay, we have a question here that says, at the beginning of the talk, you mentioned that outliers are some combination of noise, error, and real variability. And you showed that we've gotten better at reducing the error and noise. So what do you think is the most important finding, method, instrumentation that makes, that will move seismology forward in the future?
Well, as I said, this KickNet downhole instruments are really good. At one time, I thought, well, we can't do decent seismology as long as we live on the surface. So we have to all go down, or underground. However, we can put instruments underground, and we can still live on the surface to do seismology. So I really think these downhole instruments are extremely useful for understanding all the details. That makes our life much simpler. And in case of KickNet, it's a network, and it's very good. And if you look at those data, it's really very, very clean compared with what we normally see on the surface.
So Japan is probably the only place that does it systematically. I think there's what, 700, 750 borehole stations. Do you think US or New Zealand and Europe should also put sort of systematically very large borehole networks into place?
That will be very useful. I mean, in case of Japan, many of them are just 100-meter and 200-meter KickNet stations. There are some 3-kilometer kind of thing. So once you go down to only 100 meters or so, it's a different world, particularly if you look at high frequencies. Of course, Rachel used Cajon path downhole instruments, and you know, the waveforms are much, much cleaner than surface records. So, well, if you want to do something important, I think we should have a good downhole network. We can certainly go into more details.
Yeah, you have to always think about the cost though, drilling all the holes.
Well, compared with something else, I'm not sure that's that prohibitively expensive or not. Well, KickNet did it, you know. If Japan could do it, why not?
Okay, we have a question from Frederick Massian. Do slow earthquake ground motions affect a relatively wider area than usual earthquakes?
Well, at very low level. Slow earthquakes, anyway, to begin with, do not produce very strong shaking. But that's an interesting question. If you take distance attenuation, look at distance attenuation of slow earthquakes, it's probably very slow, the decay. However, it's very low anyway to begin with. So it may not, it may not be possible to really see it. But presumably, yes, if you look at the ground motion amplitude at the 30-second period, probably so, but I have never seen it.
Here's a question from Jigang Peng. Some recent megathrust earthquakes like Tohoku have foreshocks or aseismic slip events before the main shock. Do you think that these are outliers, or do you think there's some new rules for large earthquakes and for precursors? And what are some of the observations that we can make or maybe cannot make about that?
Well, I don't think that's very regular. I mean, sometimes those things can happen. And also, the slow slip before Tohoku earthquake 2 days earlier, before Tohoku. Well, also, I mean, there's a question whether that's really a slow earthquake or just a sequence of small events. So it's very difficult to really see it in any case. Only 2 major earthquakes, 2014 Ikiki and Tohoku seem to have this type of slow precursor, but we don't really see for many other events. So, well, basically my feeling is, again, the same thing, whether you see slow earthquake or series of small foreshocks, it all depends upon the structure, and it all depends upon whether things get triggered or not. So this is a part of this non-deterministic part of seismology, actually. So I don't think we expect them to happen regularly for all the events in the same way. So for some events, maybe preceded by some small events or preceded by slow event. But I don't think it's very consistent.
Did you look carefully at, say, Sumatra or some of those other big subduction zones for any possible signs of those slow earthquakes?
I'm sure someone has looked at the Sumatran earthquake. Do you know any study? I'm sorry, I don't recall anything.
Yeah, I don't
you know,
remember.
over time scales of whatever, a day or something.
So sometimes it happens and sometimes it doesn't happen.
That's right. So that's really part of our life. Earthquake is essentially, large portion of that is a chaotic system. And by definition, the behavior can be chaotic. So we cannot make very precise prediction consistently, but at least that's we need to be aware of.
Okay. Here's a question, I think, about the W phase.
Yes.
The Pacific Tsunami Warning System applies the mantle magnification and slowness coefficient methods for purposes of tsunami warning. Is it possible for effective operations and analysis to look at the different frequency content of the signals to identify tsunami or slow earthquakes from regular earthquakes? Actually, maybe not so related to double phase, but I think the question is more, how do we identify slow tsunami earthquakes from regular earthquakes from the current observation?
Okay, well, that's very easy. Well, Emil Okar sort of discussed many years ago, and we have been talking about these days. Basically, you can just measure the spectrum, but even if you can measure a very long period, 200 seconds and 5 seconds, I mean, difference is so obvious. So you can make very definitive distinction very, very rapidly. Maybe I misunderstood the question. I think it's really one of the things seismology can do very well.
One of the successes of this observations.
Ah?
Yeah, I agree. I think that's probably one of the big successes. Is
one of the easiest things we can do. But unfortunately, it's not routinely implemented. For example, NVIC has been doing a wonderful job in determining mechanism and long period moment and everything. But old-fashioned body wave magnitude, they are still determining it, but not quite routinely or consistently. So if you combine long period quantification with high frequency quantification, like old-fashioned MB, for example, that can be very useful, certainly. And maybe this is what Dr. Okar sort of emphasized some years ago. Of course, I'm sorry. And also, I forgot to mention that now some energy is routinely determined. Precise estimation of energy is still very difficult. But for this purpose, you don't need that kind of accuracy. So the current real-time energy can be really used already if you combine it with long period magnitude.
Here's a question from Dave Wald about maybe old-time seismology. It says, Hiroo, why don't we make use of first motion mechanisms anymore? They could help with very rapid source characterizations and shaking estimates.
Well, but still, depending upon how you do it. If you do it correctly, I think that's correct. But very often, fast motion can be different, particularly for very large events. You know, the very beginning can be different from the whole event. So, but certainly, I completely agree that some old-fashioned seismology is still useful. We shouldn't give up all these methods. We have now much better instruments, and we can do these things very quickly. So I think all the parameters like MB and those things have some value because we can determine it very quickly and consistently.
Here's a question from Joan Gomberg about structure. She asks if the structure in the uppermost mantle can modify the seismic waves so significantly would you expect that the structure around a fault zone, that if it's wide and gouge filled, and how would
Sure.
that impact the radiated seismic waves?
Well, again, that is correct. At high frequencies, of course. That's one of the reasons why it's very difficult to determine energy accurately for small events. However, as you go to very large events, if you look at the energy spectrum, the peak of energy spectrum can be 50 seconds, 100 seconds, a very long period. So usually those long period waves are not very strongly affected those structures. So in a way, accurate determination of parameters for small events is still very difficult. And then maybe you want to go to downhole instruments for that.
Annemarie Baltay also asked about hazard maps. And I think we all remember one of your favorite sayings is that anything can happen. And I think that's really correct. But how do we incorporate the anything can happen idea into hazard maps, especially for outliers or anything new that we might expect?
Well, it is true that anything can happen anytime, anywhere. That's to some extent, that's true. So that simply means in case of earthquake problem, very definitive consistency cannot be expected. There are so many elements involved. However, as this is the main point I want to make actually, the general property, general relationship trend is also important to know. So hazard map will tell us overall long-term general trend, I think. That's very useful. However, if you go to very short-term process, just like an earthquake, lots of unexpected things can happen. But there are ways to deal with that. This real-time system can be effectively used to deal with that. So hazard maps are very useful if people understand what it means. But if people take it as something that will tell you what will happen tomorrow, that can be very dangerous.
Okay. Yeah, we're getting near the end here. Any kind of final comments or advice about where we should be going in terms of seismic hazard mitigation?
Well, I have a tremendous respect for modern engineering. And I really think it's very important for seismologists and engineers work together to implement all the different things for practical purposes. Well, if they can fly a helicopter on Mars, why can't we implement something very fancy on the Earth so to reduce seismic hazard? So I think we really need to work closely with engineers. The modern engineering is incredibly important, I think.
Okay. I think we're getting to the end of the time, and I'm sorry we couldn't answer all the questions, but we tried to fit as many as we could.
If you can send the emails, I can try to answer.
Yeah, okay, we'll send those to you and you can answer some of the other ones.
Sure.
I guess we should end the session now because it's 5:30. I have one quick announcement from Nan. She said that there's a new social hour that's been added to the program tonight from 6:30 to 8. The previous one was very successful, and so she invites everyone to this added social hour, which you can get to from the web page. So I'd like to thank you, Hiroo, for a very inspiring talk and all the questions on the chat. So I think we'll end the session there. Thank you to everyone.
Thanks.
Thank you.